Hello, I'm Matthew DaCosta. For this project, I worked primarily on the core engine architecture, scene editor systems, and data serialization. I helped design and implement the architecture of the game engine. The game engine is highly decoupled, with each system being separated from one another. This allows us to run separate parts of the engine at different time steps. We decided to run physics and gameplay script updates 60 times per second. Our engine architecture was inspired by modern game engines. Our team had some familiarity with gameplay programming in engines such as Unity and Unreal Engine. I implemented a component-based architecture, where objects in the game are composed entirely from smaller component classes that have both data and functionality. Systems in the game then loop through objects and scenes to find relevant components. For example, the renderer searches for sprite components, which have information about the OpenGL texture to draw, the dimensions of the tile sheet, and which frame of animation should be shown. As a part of the component system, developers can create behaviors within the game. Behaviors are special kinds of components which are updated at a fixed time step of 60 times per second. The game developers can extend behavior in their own classes to create player movement controllers, AIs, user interface elements, and more. These behaviors can interact with other components on their parent objects, as well as with other components, objects, and scenes in the engine. Each game object has a transform. This is shared across all components and is used as the basis for spatial systems such as sprites and bounding boxes. Multiple scenes can be loaded and updated at one time. Scenes are independent of one another, but can interact with each other through the Scene Manager. Scenes can be deactivated and reactivated, which lets developers pause physics and behavior updates for an entire group of objects at once. Scenes can also be hidden and shown. This is useful for menu screens, where the developers may want to keep the menu loaded and only show it when it's active. I worked on the build process for the engine and game. The engine is separated into the Hudson Engine project, which contains everything needed to make a game within the engine. This includes the 2D OpenGL renderer, GLFW window setup, physics, audio and input systems, and scene and component system. The engine builds to a .lib file, which can then be statically linked into a game executable. The game projects depend on the main engine project. The engine provides a sample called DemoGame, which demonstrates how to set up and use the engine. The demo behavior contains some snippets showing how to interact with the various hooks that are called on the behavior class. The main.cpp sets up the engine, starts the editor if in debug mode, and creates starting objects. The engine then takes over the running of the game through its own update loop. To ease the development of the game, I added a scene hierarchy panel and an object properties panel to our engine's editor, which was built using the dir-im GUI library. This editor can be incorporated into a game to allow placing objects, adding components and behaviors, and then saving the current scene to our scene file. Components can define their own property panels by implementing an additional interface. These property panels are then displayed when a component is added to an object. This allows values to be changed for individual objects. To allow the editor to hook into the engine without coupling it directly into the engine itself, I also added event observers to the engine loop. If the editor is removed at build time, the engine is no longer aware that the editor exists. Little else needs to change. The editor also has the facility to pause the entire game at once. This allows objects to be set up without running the game, then the scene can be tested live in the editor. Finally, in order to allow the editor to know about behavior classes added by the game, I decided to add a component registry to the engine. This allows the game to register custom behaviors with the engine, which can then be added to objects through the editor's UI. To avoid needing to hardcode object constructors into the engine, I used standard library function objects to call no-argument constructors on components. I also use C++ concepts to ensure components cannot be registered if they don't have an appropriate constructor. Scenes can be saved from the editor, then can be loaded back up either through the editor or through gamecode at runtime. The scene's save load makes use of Neil Loman's JSON library. A scene JSON file contains properties for the scene, properties for objects in the scene, and components on the objects in the scene. Custom components can also be saved and loaded. Developers can define JSON load and save functions to allow them to save their own values into the scene file. The game can now save the behaviors data to the scene file, then create new components with the appropriate data when the scene is loaded back up.
Hi, I'm Brandon, and I'm going to show what I've done for the Hudson engine for our team. So I've created a camera which uses an orthographic projection. I also have getters and setters for position, so the developers can set up the camera wherever they want. I then have a physics manager which handles our colliders and equations of motion, and also calls the calculate time step, which I'll talk in a moment. This will update time for all our objects in every scene. So our time step class is to calculate a fixed time step. This is away from our frames per second. So this is the amount of updates per second for physics, since physics isn't based on frames. So we have 1 divided by 60, and that is the amount of updates per second we are going to pass through. Delta time is our time step value. So we have GLFW get time, which is the amount of seconds that are passing when the engine's running. And we create an accumulator, so every second we pass that delta time through. We then have a physics component, which calculates all our equations of motion using delta time, which is our fixed time step. So we have calculate acceleration, velocity, constant acceleration, and then we have a function to update object's positions based on the velocity too. We also have a collider component. This uses axis align bounding boxes. That's what we agreed on using. So we have a function and a struct. Struct holds every direction of a square, and then we calculate the position of that square in getABB. And then we have another function called AABB collision, which then returns a ball to check if two box collisions are colliding on the X and Y axis. And the developers can use this by using a vector list that I've created. So this stores every collider that's been hit into a list, and then developers can access this list and decide what to do with every collision that gets detected. I then have a text renderer using the FreeType library. This library allows us to render text onto the screen using true font style files. So I initialize it, and then I store characters by looping over every ASCII character and storing it as a texture, and then drawing it as a quad. And then I pass that through the shader to draw onto the screen. I then have also created a content browser for the editor. So firstly, I created an ARMGUI load image. This allows us to load PNGs or JPEGs for icons for the content browser. And then the content browser will loop through a directory of the current project that's been loaded into the editor of the game engine. And we can go through a directory, create different folders, and access these folders using ARMGUI drag drop sources, which create a payload of where your mouse is. And you can pick up an item and drop it anywhere you want. For example, if we go to text component, we have a drag drop target, and this is where you drop off the payload that you got from the content browser. That is everything I've done for the Hudson engine. And now I'm going to show you what I've done in action. So this is the content browser, so we can navigate the directory of the current project. You can see we've got rooms folder, texture folder, fonts folder. So we're going to go into the fonts folder, and this is the text component. So we can go onto the text component, text, and we can place it in different fonts. As you can see, different fonts change. And if we click play and start the engine, we've also got physics, so we can see the characters move. their positions update. You can see they have constant acceleration, velocity, and force, and our box colliders will also collide with different objects.
Hello, this is Connor here, and this is the audio manager of our game. What we decided on is Outland, which is a high-level audio engine, which allows compatibility with multiple file types, such as WAV and MP3, FLAC, etc. And it's cross-platform and it integrates with OpenGL well. And it's pretty nice to use the interface with the user namespace Outland. We have iSound effect control for the sound effects, iSound engine for the engine itself, and the audio stream loader to load stream loaders and decoders. Here we have a file path. This is where the sound files be declared for the multiple different types of sound files. And this is a Nenum sound effect type. These enums here are available for Outland API. And the namespace that ensures that audio is tied into the engine. If we go on to the CPP file, what we have here is the IMGUI, which means we allow for this function to work. So if the button play sound is clicked, we load the sound file with the file pathing and play the sound. Loop to true means if you want to play the sound repeatedly on a loop, and the pitch and pan manipulates the sound in a way, in the position and the volume. The set sound effect function takes an enum value from this function here and sets a boolean if you want to enable the sound, in which case this is true. Here we declare, we create the engine, the Outland device, Outland audio detect, which detects the available sound driver, which in which case the direct sound is our available driver. If it doesn't recognize it, it drops the engine. This is to prevent memory leaks. This is the destructor, and it does the same. These comments are to help the developers understand more how the audio manager works. Right here, it declares a sound, the engine plays the sound, and all the parameters here. If sound sounds, pushback sound. Sounds right here is part of it. Standard map, which tracks multiple sound files, which is done behind Outland's low level, behind the scenes, which is another nice feature about the API. Total sound, but is playing. Yeah. And if it's playing, we pause the sound and the loop is false and the pitch pan's not true as well. Else we resume it and it's back to its original state that was on the play sound function. This is to stop all the sounds in the sound pathing. It takes the first element and the second element, and it's for loop, which stops all the vectors and clears them, stopping all the sound files, and the engine calls from that. Load it, we add the source from the file, and we reference the vector sounds, and we add that into the vector. And another catch error checking. We unload the file so the engine calls remove sound source, so we remove the sound file out all the map if we don't want to use that one. Is the sound file load? We check the map to see if we set the position, we set the volume, the engine gets the volume, and the sound is set the volume out to the file paths. And down here we set global volume for the end. Examples of how the audio gets called is, for instance, the boss right here. And we call a sound file which describes these, for example, necromancy, rising animation sound file of the dead rising, and Hellfire Wave is a sound of the fire. The door, we call the sound of a door as well. This will get called by audio dot and the function play sound, for instance, which will get declared here.
Hello, I'm Bailey Atkin, and this is my contributions to the Hudson engine as well as the Trials of Amit game. So for the engine itself, I have been working on the input manager, which uses GLFW to recognize and set key inputs so that the developers can easily access and set the inputs to actions that they want the player to perform. The keys themselves are stored in a struct called key, where the ID, name, actions assigned, and a boolean that says if the key is down are stored. To start recognizing key input, a bind callbacks function is called, where it will set the callbacks for the keys, the cursor position, as well as the mouse buttons on the mouse. This is called inside the renderer before ImGUI is initialized so that it can work alongside the ImGUI window. If it is called anywhere else or after the ImGUI is initialized, the ImGUI window itself will not recognize the inputs, and overall it just wouldn't work. The callbacks essentially tell the system that it should start listening to for input from the mouse and keyboard and calling the callbacks set in the input manager. Keys can be bound to multiple actions, so let's say in a menu, for example, W can be pressed to go up in the menu, but in the game it can also be pressed to move the player upwards. So when the devs want the system to know if an action has been performed, they will just call the getActionState function, which will return a boolean from key down of that key corresponding to the action, saying if the action has been, well, if the key corresponding to that action has been pushed down. Key actions themselves can be set and saved. So for example here, spacebar is set to attack, but if I were to set it to something like jump, it's still there. Save the changes, and then next time the editor is run, it will still have those changes. It can also be unassigned, and again, much like it being saved when it's set, it will also save when it's deleted. And that is basically how the input manager works. Now for the boss, Anubis, inside the game, the boss essentially rotates through 4 different attacks, which are as follows. So the lasers will already be created in the room that the boss is assigned to, and essentially the boss will look through the scene for game objects that match the laser, well, the laser type, and it will start the charge function of the lasers. And this essentially changes the current state of the lasers to charging, which will start the animation and start colliding with the player, and if the player doesn't dodge in time, it will damage the player. The charge up time and the animations give the player ample time to dodge, and that's essentially how that works. Necromancy will just simply rise a mummy from the dead. Hellfire is an attack where it will start raising fire beneath the player's feet 3 times in a row. There is a charge up animation for this, so the player knows when it's happening and knows when the fire is about to hit them. And so they must move out of the way, otherwise they'll get hit with the fire. And then there's the Locust Swarm, where the boss will summon 3 Locust enemies to charge at the player. They die upon impact, doing a low amount of damage. But if the player attacks them before they hit the player, they won't take any damage, and the Locust will just simply die. They're one hit, no matter what, simply because they're just a frail enemy. Each ability has timers, as well as there being a general attack cooldown, so this gives the player a lot of time to dodge out the way of, what the boss is throwing at them, as well as giving them time to reposition, and it stops the boss itself spamming abilities. So say, like, it just doesn't stop using the lasers or doesn't stop spawning zombies. This is to prevent that. It's for the boss to know which ability it wants to do next. It will simply just look at the timers, and then if all timers, are up, it will prioritize the laser. If the laser's on cooldown, it will choose between Necromancy, Raising the Dead, the Hellfire, or the Swarm of Locusts, and it will just choose at random either of those 3. And that's essentially how that works. For damaging the boss will be shielded during its initial attacks, so the player has to survive 5 attacks, and then there will be a damage phase. There is a shield indicated by a golden tint on the boss, and once that shield lowers, it will remove the tint, and that is when the player knows they can damage the boss, and they will just have to walk up, hit the boss for a set amount of time, and once that set amount of time is over, it will just transition back to the shield state, where it will attack the player again, and it rinse and repeat until the boss is dead. And those essentially have been my contributions to the game and the project.
Hi, I'm Harvey, and my main contributions to the project were the AI agents, the menu buttons and the settings buttons, the doors to get to the next rooms, and the camera dollies. The AI agents has multiple different states, which it cycles through in order to do different actions. The onCreate sets up all of the sprite components and physics and colliders, and then gets access to the player, and the onTick swaps it between states depending on where it's been called. The collision check just makes sure that it doesn't move outside of the walls by calling the inverse velocity function. The animate runs it through the animation cycles depending on where its current velocity is heading. The seek and wander functions work roughly the same. Just the wander function is handed a random target, whereas the seek function is handed the player's position. The AI attack function accesses the AI attack script and calls based off the facing direction. The inverse velocity just does the inverse velocity to where the AI is currently facing. when the AI is dead, it calls the AI dead state and changes the current sprite and spawns an object if it's in range. The take damage just takes damage and flicks the AI to a different color for a frame. The random target selector just picks a random target position in between bounds that are close towards the current position. The get and set the player positions, and the move function just moves based off the given parameters. This is just for ARMGUI. The menu buttons are passed in they're passed in a text to render onto the button. They're the next scene that they'll go to and a reference to the input manager. So they'll set all of the text components up in the game object, and then when the button is clicked, it will send it to the next scene. The settings buttons work the same, except from they have multiple different options. So they set up the resolution text and buttons, the audio text and buttons, and the full screen text and buttons. And then they work the same as when they're clicked. They will then either forward the resolution or they'll go back, and the resolution is based off a vector array of different 16:9 resolutions. And then they will change the window size and buffers to change the resolution. And then full screen does the same, but if it's running in debug mode, then it'll ignore it. Whereas if it's in the release mode, then it will change the game into full screen. The doors component I created and then had a bit of help from Brandon B. Due to him making the room component, so it was quite tightly put together. So it will check if the player has collided with it, and then once the player has collided with it, it will generate a new room based off a random number, and then it will set that to the file path, and then choose a random number room from there. And then it will delete all the objects in the old room, and then spawn a new room, and then move the player back to the bottom of the screen. The camera dolly works just in the engine and will be based off the arrow keys movement, so you can move around world space, but only within the engine.
Hi, I'm Kenny, and I'm talking about my main contribution to the project, which is the ability class, which has the basic ability class, which is the parent class, which helps us make the abilities, which are derived from base ability class and inherit the properties and methods of the base ability class, and the ability holder, which is what manages the abilities and is attached to the player game object, as seen here. Now, essentially, the base ability class has usability, the functions usability and deactivability, which will take in a scene, which has the parameter current scene, which is what is used to find a player or enemy that will be affected by the ability. We have enum's ability state and ability type. Ability state, which tells us the state of the ability, whether it's ready, active, or on cooldown. And ability type, which was made by Chris to help make the UIs of the abilities. As for the ability holder, like I said before, it helps manage the abilities. This is what this is essentially where the abilities work. So in the ability holder, it's onTick, our version of update function, essentially put where the magic happens. So if the ability is ready, and we press the key to activate the ability is active. If the ability has been active for its active time, it's then set to its cooldown, and if its cooldown is over, we go back and say the ability is ready. That's essentially what the ability holder does, as well as holding all the abilities that have been made by the ability class. And as for the abilities, we tested out role to make sure that the class was working, the tool was working. And this was finished by Chris, which is essentially the player rolling and entering a state of immunity for a set amount of time. Stun is an ability that affects the enemy, freezes the enemies for a set amount of time, allowing the player to attack or do whatever. Rage affects the player and allows them to have increased attack speed and increased damage for a set amount of time if they've reached when their health is low. Heal is pretty much self-explanatory. The player heals for a set amount. And Room AoE is, AoE stands for Area of Effect. So Room AoE is a damage ability that affects the room and just affects the enemies that are in the room. So they take damage and the player is fine. And that's it.
Hi, I'm Chris, and I'll just quickly run you through everything that I did. So, my main contributions to the project were the player, the weapons, the pickups, the room collisions, in-game UI, and the pause menu. So, the player has lots of functions on it. So, it starts obviously by creating the physics, the colliders, and the sprite sheets, and the UI around it. As well as this, it has functions for the passives to access when they are picked up on the pickup behavior. As well as this, there's take damage and there's death checks, obviously to see if the player's still alive, as well as wall collisions, which are set here. It also has pause functionality, so in the player it checks for the pause and it will make a like a pause manager sort of thing that we set up. As well as this, it obviously does the direction and the moving direction and the facing direction, which are used later in the wall collision and the movement. It has attack functionality, which is done through a class system. As well as this, we have got down here all the movement scripting. It creates 3 separate UIs, so the weapon, ability, and health UI. So the health bar, it shows what ability you currently have and the weapons. This is the wall collision code, so it's just checking for the walls, and it does inverse forces. So it will set the player to go the opposite way to the way it's facing, and it will move the player back at last frame and set its velocity to 0. As well as this, it's obviously got the sprite sheet animation for when it's moving. And I will now show you the base weapon class. So the base weapon class is a class-based system that has all of the functions that every weapon will have, and then we wanted to specify a bit more because we've got melee and range classes. So in the base weapon class there is just a base attack, but in the ranged we have got new variables. So like if I show you in the bow, we have got this attack that passes obviously through more values because it's a ranged weapon and it's sent into a bow and stuff like that. Each weapon has 5 tiers which are set here, and so when the player like picks it up off the floor, it will obviously set the level of the bow, and that's just done through the pickup system as well. The projectile system is like set so it gets the player's direction and all of the values and will assign them to the projectile, and then obviously fire it in the way the player's looking. As well as this, it handles the collisions with the enemies or the chest, which are the 2 things it can collide with currently. Let's do the pickup behavior. So the pickup behavior was obviously hooked into the pickup weapons and the passive pickups, as well as the ability pickups. So basically, when the player interacts with one of these pickups, it will either like set it in there, or it will set the ability, or it will change the weapon. So apart from that, we have the abilities. So we've got the ability holder, which was I helped set up. So basically, we wanted it in a base class like ability system. So this is called, obviously, in all the base class, usability and deactivate ability, and this is just the check and the timer for it, so the logic behind how long it takes to reset, and all of them have unique values. So I did the roll, which will set the player, obviously, the movement speed higher and set the god mode to true to give it some unity frames, and I also did the stun, which accesses all the agent AI and will set the color and set the speed to 0. As well as this, I did the pause menu, which sets up a pause menu holder and then will wait for key presses. And finally, we have the chest system. So the chests work the same. They just drop a random weapon from the object pool of weapons. So weapon, pick up weapon, it has a object pool down here, and it's got a higher percentage chance of dropping the lower ones. Finally, we have all the UI. So I'll show you the player health UI. So it literally just on the tick checks for the player and changes it, and that's also like the weapon UI. It does the same thing. It just checks what weapon the player has and changes them.